Is this the big one?
This is you sit next to Milky, but beyond that, it's good.
Well, it's a distinct pleasure tonight to welcome back to the area and to Mound our speaker, Dr. Robert Bowman. He came here in '69 and stayed through until he left in 1984. And he did a lot of work here, particularly on the topic he's going to be talking about tonight, on study of hydrides and tritides in particular. And he went on, left Mound, and succeeded to continue in that career, and he finally retired as a workaday guy, but he's still consulting with Oak Ridge. And he's going to speak tonight on some of the nuclear magnetic resonance studies he did here at Mound on NMR. So let's welcome Bob back.
So my understanding is that Don's going to handle the slides. But yeah, I stayed just a little over a tritium half-life here. And we're at the end, so good. We're ready to get back to the beginning. I'm assuming that most of you know that hydrogen has 3 isotopes, protium, deuterium, and tritium. The difference is how many neutrons they have, and that tritium is a radioactive one, and that's what Mound had a lot to do with. And so that photograph is about 1981, it said, and that's when I had a coat and tie on, which is a very rare event then, and even a rarer event now. So, and I bounced around a lot, not always doing Metalhydride, but rocket science and JPL, but also at Aerojet, some work on semiconductors. But hydrides were always my interest and love, and in the last few years I was able to work for DOE on new hydrogen storage materials and applying the advanced solid-state NMR techniques that have evolved in the last 20 years to give you high-resolution spectra in solid. I'm not going to cover any of that today. If anybody happens to be interested, I'm more than willing to talk about it or send you a paper or whatever we were doing. Okay, Don, can I have the next one? This is what I'm going to cover today. At first, we're going to say, what are Metalhydrides and why does anybody care about them? And basically, that's kind of an overview of what they are and how they're very general view of their application and what was of interest at Mound. I will then try to give in a few minutes a tutorial on NMR, specifically as it related to the helium-3 isotope and tritium, and how to tell the difference between trapping or retaining helium in the solid and in gas bubbles. That's one of the things we did a great deal with. Most of you probably are aware that NMR is what magnetic resonance imaging is, and I suspect from the age of folks here, you've all been in an MRI at one time or another to have something examined. I've had my turn in there, and I decided I'd much rather do the experiment than be in the experiment. The way we did NMR here at Mound is very different than resonance imaging, but the basic physics is the same. NMR were done on a number of tritides. The 3 primary ones that we worked at Mound is lithium tritide, the ionic salt material that has a lot of self-decomposition, which I'm going to describe. Uranium tritide, which is very strongly paramagnetic, and palladium tritide with temperature dependence, relaxation times. A lot of this work was done by George Abel and so forth after I left Mound in the late 80s. I'm not going to cover it tonight, but it was done, and there are papers published on that. After giving some examples, I'm going to give a few minutes about the folks that actually did the NMR work and the hydrides. A couple of them are still here, or here in the audience. I don't know where the rest of them disappeared. I was, as Don said, in California for over 25 years, and I think people migrated somewhere else. Then I'll give a couple of slides in summary of what NMR and hydrides are in current times. Then there's an appendix, examples of things that I just don't have time to cover, and a list of the papers that were published. Don has that, and I left a set of papers here at the museum, so if people are interested, for some arcane reason would like to see what was done, they're available. Okay, Don? Okay, what we're going to cover are metal hydrides. These are basically solids formed by hydrogen gas reacting with metals and alloys, and they're represented by their pressure and composition isotopes. I'm trying to show in one slide all you need to know about metal hydrides. I don't know if I'll succeed or not, but let me try. The alpha phase, this is a low concentration. If you recall, hydrogen is a diatomic gas, two atoms bonded together, and at the surface of a solid or a metal, they can break apart, and the hydrogen atoms bond within the material and go into the open spaces, voids or interstitial sites. And at low concentration, basically they just dissolve in the metal, and that's called the alpha phase. This is a concentration of hydrogen in metal. Typically it's 0.1 or lower. On the other hand, if you keep exposing metals to more hydrogen gas at appropriate pressures, you can actually fill up the material, all these interstitial sites, up to as many as 3 hydrogen atoms per each metal atom. So it's very concentrated. There's often a phase transition, you get changes in crystal structure, so there's actually, and very different property. You take lithium metal, this is a conducting metal, you react it with 1 hydrogen, form lithium hydride, it's an ionic salt. And there are a lot of examples, but many of them, things like uranium remains a metal. But the characteristic, this is the pressure, this is actually increasing by powers of 10, so this is 100 atmosphere pressure and concentration. And these are isotherms. This is 0 degrees C and 25 degrees C and 100 degrees C. And what you have, this is called the plateau region. When you're converting between this alpha phase and beta phase and going from one to another, according to laws of thermodynamics, a relationship called Gibbs phase rule, you'll have a constant pressure at a temperature. So this region here is between the two phases. If you go, typically this is an idealized hydride, it's not necessarily a real one. It's sort of like lanthanum nickel 5 as far as where the pressures are. That's an intermetallic that had a lot of interest and use. But you see, you go up, there's a critical point where hydrogen just dissolves in the metal without any phase change. Palladium will do this at a couple hundred degrees C and around 100 atmospheres pressure. So generically, the other thing is if you take the pressure at a different temperature and plot it versus reciprocal temperature, you get a linear relationship of log pressure versus temperature, and that slope is the heat of reaction, the enthalpy divided by R. So this is an exothermic reaction, releases heat, and the intercept at infinite temperature is related to the entropy. So that's the, so you got thermodynamic properties determines this, and so this is the overall what hydrides are like. It doesn't tell you their interaction, but with their gases. Next on. Okay, so why do we care about this? We're talking about hydrides, and I'm going to put in parentheses tritide because it's just another isotope. What you have is compact, low volume storage of the hydrogen isotopes. In fact, the concentration at room temperature is almost always greater than liquid hydrogen at 20 degrees Kelvin. So it's a very efficient way to store hydrogen. Now, their gravimetric densities are relatively low. That is, because you've got a metal, you're putting hydrogen in a space. So if you have something like uranium or other heavy metal and not much hydrogen in it, maybe only 0.5 to 1 weight %. If you have lithium, it's on the order of 10 weight %. But still, you can get a lot of hydrogen per unit volume, but you have the host material. You get these large pressure changes with temperature. I showed you on the last one, you can go from a 100th of an atmosphere to over 100 atmospheres in 200 degrees change in temperature. So this can be used for pressurizing systems or for collecting gas. You can desorb and release extremely pure hydrogen. You know, I showed like 6/9 pure hydrogen. If you have other gases, you can put that in. Or you can take tritium that has no helium-3. If the material is stored and the helium-3 that comes from the radiation decay is held within the solid, then you get pure tritium, which is often of interest for a lot of reasons. And finally, that heat of reaction can produce heating if you're absorbing gas or cooling if you're desorbing it during the process. So you can actually do mechanical work. So there are heat pumps and other things that are looked at over the years for these things. So again, The applications of hydrides are storage and safe transport of isotopes. In fact, Mound in the late 80s and 90s was doing that as I think as a business plan, or at least working with a fusion and other commercial technology. Onboard storage of hydrogen for vehicles, either internal combustion or fuel cell. That's what we've been looking at for the DOE in the last few years as alternative fuel systems. They're running cars on gasoline, run a fuel cell with hydrogen storage, and you can do hydrides there. This compression and liquefaction, you can do Joule-Thomson refrigeration, forming liquid hydrogen, cryogenics. In fact, that's what I did for 10 years at JPL, was developing a hydrogen absorption cryocooler for a space mission, which actually launched in May, called Planck, to provide cooling to a detector going out to deep space to measure the radiation from the cosmic microwave background radiation. Another topic if you want to talk to me sometime about it. There were actually another thing, not only will hydrogen gas, but you can do certain hydrides react with batteries and make rechargeable nickel metal hydride batteries that have actually been commercial, replacing a lot of the nickel cadmium batteries. So this was being at least a technology. There are lithium ion batteries now, but still nickel metal hydride batteries are being considered and even being utilized in some of the automobiles that look at performance. And finally, the separation, purification of hydrogen isotopes, and these typically involve palladium alloys, but other metals as well. So those are general applications. Don, the next one. Okay, having kind of given an overview, what was Mound interest in metal tritides and hydride? Well, certainly in house processing, material synthesis. As far as I know, at least from the 60s up through closure, there was uranium tritide reactors and storage systems. These are U-beds for experiments, for preparing different materials, palladium for separation and purification systems. So there was in-house use of tritide. There were a variety of projects for the design lab, Sandia, being done at Mound. In particular, one of the things that I was involved with was the mechanisms and mitigation of self-radiolysis, decay in lithium deuteride tritide. And that's what I'm going to describe in a little more detail in a few minutes. There were pyrotechnic components using titanium hydride, trying to avoid that, and other components and other applications of the hydrogen isotopes. There was tritium storage and shipping container in the late 80s, I guess, and early 90s. That was being done after I left Mound, but I know that, I saw the video, I saw the tape, so I know that this was being done. And now when I was here in the mid-70s to 80s, there was the first energy crisis. You may remember when oil got to $1 a gallon, everybody was all upset. And so the DOE, Basic Energy Science, funded hydrogen work. And Mound was lucky as one of the only weapons labs to actually get BES money to study metal hydrides as a system. And that was done here. We did a lot of NMR work on the so-called exotic hydrides at the time. And so I'm not going to cover that, but it is part of what we did here. Okay. All right. Having given you now in 10 minutes or less what metal hydrides are, I want to tell you what's NMR. Okay. I mentioned we're not doing magnetic resonance imaging of bed, but it is a spectroscopy based on the splitting of nuclear spin. I is a spin quantum number levels in an external magnetic field, and where there are transitions between these levels at an RF frequency depending on the typical magnetic field. And we're going to focus on the spin quantum number 1/2, things like protons or tritium or helium-3. Down this little chart here, this is a magnetic dipole spin 1/2. You can think of it as a little spherical charge rotating. And there's a quadrupolar one, spins 1 and greater. Deuterium has spin 1, lithium 7 isotopes spins 3/2, and so forth. Each will have a quantum number. This is the magnetic gyromagnetic ratio. This is a ratio between the RF frequency and the magnetic field where the energy level is. So each isotope has a unique value, and that means you match a field and frequency, you see a resonance at that particular one. So if you're at 0 magnetic field, basically for spin 1/2, as an analogy, not necessarily the physics, but you have spin at 1/2, you have 2 energy levels. You have clockwise and anti-clockwise. It's angular momentum. Just think of it that way. And you have 1 billion trillion of these little magnets spinning around in 0 field. They're equal energy. There's no energy difference, and so there's no magnetization. If you apply a magnetic field, the ones that are going to be lower state energies, let's say the counterclockwise, lower energies than the clockwise, so there's going to be a population difference, and what you'll have out of this is a net difference in energy, and that promotion by putting RF to take the ones from the low energy to high energy to equalize. That's what NMR is all about. Okay, so the next slide, Don. So what we do, and most of our experiments were a pulse experiment. And the pulse experiment is that what we had is this is the applied magnetic field, and the net magnetization vector here, and this is precessing in that equilibrium magnetic field, that little, and if you then hit it with RF and you flip those spins, what you do is the RF, this is B1, at a right angle to the applied magnetic field, is that for the period of time, that's what this pulse is doing, and for a time, it will, the magnetization, the net magnetization will progress here. If you go 90 degrees or pi over 2, what you'll have is you'll have it in, magnetization flipped here, and then if you turn it off, what it's going to do is going to ring. It induces a voltage in a pickup coil. That coil detects a signal as a function of time. The time constant is microseconds to a few milliseconds, so an oscilloscope or a story will pick up the signal. And so what you'll do is that you can continue to pulse longer, and you can actually flip the magnetization so it's inverted. That's a pi pulse. But the pi over 2 pulse perpendicular, that gives you your maximum signal. Now what happens is you turn that off, the spins go back to the equilibrium in the applied magnetic field, so the magnetization will ultimately come back. But there are a lot of dynamics within that spin system, and that's what we were monitoring with our NMR experiments in order to sort that out. Can I have the next slide? Now this is what we call a spin echo, and a spin echo is a fundamental concept where we use this pi over 2 pulse, a 90-degree pulse, separated by a period of time by a pi pulse. And what we get is that we bring the spin back with a time constant T2. And this is the pi over 2 pulse with the magnetization. Here you wait time, and you go pi, and you give it a pi pulse, and then you have a signal form. And then here's this magnetization. And what you do is you give it the pi over 2 pulse. That's 1 to 2, and that puts the magnetization in RF field. Now what happens is it doesn't lose the energy, it just dephases all these magnetization. And now if you wait just long enough, the signal will disappear. You apply this 180-degree pulse. It basically, the spins tend to disperse. You flip the field, they now keep moving, but now they're moving back and they'll refocus. And what they'll refocus is, they'll refocus back opposite signs. So this one was pointed here, this one comes. This signal is not a phase detection, just a voltage detection, so it shows the same sign. If you're doing phase-sensitive detection, the signal will be inverted. And the time, you then would do this for different time. I'm sorry that when I kind of copied over things, this is 2 tau over T2, that time constant. The amplitude, you can get the time constant. So you measure a time constant for this process. And so that's what the T2 spin-spin relaxation time is all about. There's also a time constant related to the system return completely to equilibrium. That's called the spin lattice relaxation, lattice being degrees of freedom not associated with the spin system. And you can measure that in a different manner, which I think I have listed in the next slide. Right. So you have to do the spin lattice of T1 by 180. You invert the magnetization, you wait a long time, and then you apply a 90-degree pulse, and you bring the magnetization back. Then you repeat the experiment at different times. The T2 you can measure from the decay time of the line shape. It's called a T2 star, or that spin echo, the T2 prime. Or there's a technique by 4 guys at Carr, Purcell, Myboom, Gill. Purcell was a Nobel Prize winner back in the discovery of magnetic resonance in the 40s. But this pulse train of echoes, and you get an extended time. And basically what this does is it gets rid of a lot of incoherent dephasing and gives you the sense of the longest live spin-spin interaction time. So having done these pulse measurements, what you collect is you get a signal amplitude that's proportional directly to the concentration. Now depending on the species and concentration, you can typically measure from 5 to 20% of the intensity. There's a lot. Often if you can really do better than this, but when you have things in low concentrations or your accuracy, but you get the line, so you get an amplitude, a concentration, and you get this T2 relaxation time, or spin relaxation time, or spin lattice relaxation time. Now for the spin 1/2, things like hydrogen or tritium or helium-3, the magnetic dipole interactions dominate that. Particularly if the spins are sitting in a lattice in a position, the geometry determines what the T2, called a rigid lattice, and you can calculate that from first principles from geometry and compare that to what you measure, so you know if what the spins are. And you can actually analyze that in many cases to get more information on the geometry, the locations of the spin. But if you now the next slide, we talk about that in general. You have immobile atoms. You get T2D, the dipolar interaction, rigid lattice, approximately equal to T2, and these are all about the same, typically on the order of 10 microseconds decay time. Might be 20, it might be 5, but something depending on. But they're orders, and it's the double arrow means orders of magnitude. This T1 can be milliseconds to hundreds of seconds. All depends on the environment, how long it takes the spins to lose their energy. On the other extreme, if you have a bulk gas, like hydrogen gas in a bottle, and now they're moving around, it averages all out. The spins can't they can't transfer their spin internal energy very efficiently. It's only the T1 process that determined the T2, the spin time. And so now the rigid lattice time is orders of magnitude below what these time constants are. And this T2 star is typically the inhomogeneity of your magnetic field. You put a magnetic field in and it's not homogeneous across the sample, you'll see an effect. But if you do like a Carter cell sequence, you can average that over. And so that the T2M is about equal to or just slightly smaller, within a factor of 10 of T1. Now, the intermediate case, which is many of the things that are actually of interest, is the mobile atoms. If you have atoms sitting in a lattice and they're moving, while they're moving at rate they're hopping or rotating, you have certain motion, that will interfere with these phasing times, and you'll get a complicated relationship where these will belong there. The other example is that if you have very small gas bubbles, very small being under 100 nanometers, under 1,000 angstroms, now you've got walls hitting there, now defacing, so you can utilize that to analyze gases trapped in a bubble. So these differences can be quite large, and depending on doing an experiment, you can sort this out. There's sort of a principle of how fast does things have to move before you can get out of being a rigid lattice and seeing them. And basically it's a diffusion constant, about 10 to the minus 12 centimeters squared per second. To give you a perspective, diffusion in water is about 10 to the minus 6 centimeters squared per second. So it's several orders of magnitude slower than what it is in water. Motion of water molecules when you can actually see it in an NMR experiment. So you can use NMR to study diffusion by looking at relaxation times over a wide range of temperature and actually analyze that. We did a lot of that measurement here on different hydrides when I was here, and the folks continued that for several years. But again, it's a different topic than I wanted to try to cover tonight, but it is a very powerful tool that NMR can be used for. Okay, here's a picture of me actually sitting at the spectrometer, and I sat at the spectrometer a lot. Kind of night and day, I think, for a time period. This shows the electromagnet. This is a sample in the middle of the magnet. There's the RF coils in there, and this is actually tube for gassing to variable temperature. This is the oscilloscope, digital scope. We had a fast digitizer. It doesn't show the Polaroid camera. We take pictures. I'll show you a little bit of what we're doing there. But there's temperature controller. We had RF sources over here, and this was, all these measurements were done in room R112 in the no longer existing R building next to the no longer existing SW building, this open space. But we spent a lot of time in there, particularly Alatella and I over the years. And, so I did take data, and it's proof. At least one photograph showed. Okay, next. And here's the samples. Now, all the samples we looked at were the hydride or tritide that I was involved in, were sealed in glass tubes. This is a 7mm glass tube, and this is a 10mm glass tube. They were evacuated and sealed. These happen to be some hydride samples that I still have in my personal inventory from years that I took a picture of. But the tritide samples, there were actually a fair amount of tritium, 100 to 1,000 curies of stuff, and they were stored in ovens or freezers in SW building for a period. And for several years, and we would take them and do NMR measurements. Maybe some of you remember me carrying containers or stuff, and we go do that. But we're recording data, and I'll show you in a few minutes some of that data. Okay, Don, next one. Now this is an example of the kind of data we took. This happens to be what I found in my old files, some proton relaxation time data for vanadium hydride, VH 0.95 at about 48 degrees C. And this is a spin echo measurement here. This is the actual with a long delay. So this is the spin echo signal. This is with short pulse. What we did is these signals were collected and we shot them with the camera, and then we would plot the amplitude and that gave us from the line shape here about 0.08 milliseconds for the T2 star and about 7 milliseconds for the T1. This is the car per cell train. We're in between here are pi pulses, and you see the decay, and we plot that at 1.2. This is one of the case C samples. Turned out it's from diffusion. Hydrogen atoms diffusing within that solid. We measure this as a function of temperature, and we can measure different frequencies and then analyze it to take the data. So, but whether we were looking at hydrides or tritium spectra or helium-3 spectra, these were the kinds of things we took. And I just want to point out that we did these measurements with a Polaroid camera and digital. And we literally used hundreds of packs, 10 packs of film over the years. Well, I don't know how many, but we went through a lot. That's how we took the data. Nowadays, there are more computer things collected and so forth, so it's a different technology. But that's what we did, and those were the kinds of measurements that we actually performed. Okay, Don, next. All right. Having given you a little bit what the NMR is, I'm going to talk about helium-3, and then we're going to talk about tritium. The reason that we follow through the helium-3 is that it's a non-destructive technique, so it allows us to do long studies of tritium aging effects in material. And we could do quantitative or semi-quantitative measurements of helium content in the different materials, so we could then compare that with data measured by destructive techniques, volumetric gas analysis, mass spec. The NMR is not extremely sensitive. We need something on the order of 10 to the 20th helium atoms at room temperature to get a workable signal. To get relaxation times, we needed at least a factor or 2 more. The outcome of that is we couldn't really measure samples till they had actually had 3 to 6 months of tritium decay. Many of you may remember the half-life of tritium is 12.3 years, and so about 0.5% a month of the tritium decays in the helium-3. So you have to kind of wait and keep doing that. What we would do is we would measure the relaxation time. They were generally non-exponential, so what we would do is take the average value using the 1/e, the exponential time constant, to represent the kind of the average data. Most of the helium-3 measurements we did were at room temperature. We did low temperature measurements on uranium Tethy and some palladium Tethy here at Mound. Harry Weaver at Cindy Albuquerque did some fairly extensive variable temperature measurements on titanium Tethy. But in principle, it could be done with others, but they weren't necessarily the intent or the availability of time or samples to do that. Now, there's a funny symbol here. I guess somewhere in the translation the programmer software didn't like it, but I wanted to just point out the helium-3 measurements on tritides were actually done in relatively few locations. Los Alamos in the very early 60s did a few measurements on lithium deuteride tritide. Lawrence Livermore did work in the mid-60s, the early 70s. I'll show some of their data on lithium hydride they irradiated. Sandia Albuquerque did data, and that's where Harry Weaver was in the 70s. Sandia Livermore in the 80s did some, and also George Abel, when he was here at Mound, went out there and they did some joint experiments in the late 80s. And then we at Mound started in 73 doing measurements and actually ran up to just about before Mound closed with George. And so somewhere around 1990, 1991 was the end of NMR of Metalhydrides, or any tritium or helium-3 measurements that I know of at Mound. I don't know when the spectrometer disappeared, but it was sometime after that. Okay, done. Now, this is an example of the lithium, hydrogen, deuterium, tritium. Now, this is, again, remember I mentioned tritium decays to helium-3, emits a beta particle and an antineutrino, and has about 18.6 kiloelectron volts of energy. So it's energetic, and tritium turns to helium-3. If you recall, you form a hydride tritide, you got a nice chemical bond between lithium metal and a hydrogen atom. Well, helium doesn't have much chemistry. There's a lot of chemistry going on, so you're wondering, well, what happens to that helium? Well, that was an issue with these materials, and here's one of the problems that they had. This was measurements done at Lawrence Livermore of different samples of lithium deuteride tritide, published in a paper by Clark Sowers, and there's a lot of data elsewhere, including measurements here at Mound on samples, but this is a representative. At room temperature over a period of time, this is volume expansion. And we're starting with an original size sample, be it a pellet, and it would expand 20, 30, 40%. Well, if you're trying to contain something like that over a period of time, that's not very convenient. And so there was a lot of concern about how you would handle these things in long life systems, and what you could do to mitigate them. The other issue is, well, when you had, now this is helium release, so you got that, and it would see outgassing. There would be helium coming out in the system. That also didn't want to have that floating around in your system. This is different temperature and different concentrations. So 320 degrees C with 30%, you could get percent of the helium foreign being released, 30 or 40%. So there were a lot of questions and interactions going on about what would happen here. And so first the people at Lawrence Livermore were doing NMR measurements, and then we got involved doing our own measurements here. So Tom got next. This is actually work from Clark Sowers' group in the late 60s, published in 1970, where they looked at a simpler problem first. They took lithium hydride and took gamma rays and irradiated, and it got so many gigarads of radiation. This is gigarads of radiation at different radiation temperatures. And what they found from their own measurements and doing NMR, that they were seeing hydrogen gas and lithium metal forming, and the concentration would change. This is the swelling that they would see at low doses, and this is the radiation temperature, and that would peak between about 125 C and 250 C. Lower temperature, it was slower to come, even at fairly heavy doses. These are in gigarads, and I forget whether it's 1 gigarad is equivalent to a day of tritium decay, or a little less, but it's something on that ballpark. And so in a few days, but if you took material hot enough, over 300 degrees C or so, basically you were having no real swelling to whatever was going on. But they also took samples, and these are SEM images. And at 1.3 gigarads at 120, they got 5% swelling, and what they have are really small bubbles. I'm afraid they don't repeat, but they're roughly 7.5 nanometers, 75 angstrom. However, if you were at 220 degrees C, now these bubbles have grown so that they're 57 nanometers, 570 angstrom, and they're actually cubic little bubbles. So lithium hydride, the cubic material, and so there was a correlation that a bubble size and NMR relaxation times that Clark Sowers and his folks work out on a hydride. Well, the next slide shows data we took at Mound, and what we have are, this is pure lithium tritide. We were impatient. We wanted to understand what happened in a relatively short time. We didn't have 6 or 7 years to sort it out, so we were. And so these are actual spectra. This fast decay, that's the tritium signal with, I'm sorry, like 10 microseconds. This is from the lithium, or from the tritide anions that are sitting in the material. This decay, the long T2, this is from tritium gas. And when we extrapolate that, the initial amplitude tells us what fraction this is of the total amount. Now, we didn't compare to the signal here, but we actually used the water reference signal and converted that to amplitude. This is the lithium NMR signal that we obtained. This is lithium 7, and this is the lithium cations in the solid, and the bumps are from lithium metal. It actually, the difference between a metal and a salt is a difference in the frequency, and there's a beating here, so this is the lithium metal. And we could tune our resonance frequency and measure the amplitude of that. And then this long decaying, all the helium is a long decaying line, about half a millisecond with a time constant, and no real sharp time. This is actually just not the signal, just from the changing the bandwidth to narrower, so we get less noise to take it. And so this would be the helium-3 signal from a sample. Now, I'm afraid this next chart's going to be a little hard to see, but this is the amount of trapped tritium at different storage temperature. And the bottom one here is minus 40 degrees C, and we stored material and we see no trapped tritium. There's no damage, no formation of molecular tritium. At room temperature, you see this fairly fast decay. There's actually a couple different samples in this, and we see that there's scatter in the data, but there's a trend that there's up to 7 or 8% of the total amount of tritium in the sample is now trapped in gas bubble. If we go to 75 degrees C or 100 degrees C, we're getting somewhere between 15 and 18% of the tritium is now not in the solid phase, but in the gas phase, in these bubbles. And the next, what we did is we actually took the storage temp from room temperature up to 200, and we measured the total amount of concentration, and then we looked at the relaxation times. The T1s were typically 300 to 400 milliseconds, and then we looked at the T2 time, that ratio. There's a correlation between the wall relaxation. This is the correlation Sowers group did. From that, we determined that the average size of a bubble at room temperature for tritium is about 5 nanometers, increasing up to 60 nanometers at 200 degrees C. We get the same correlation in the tritides that Sowers had found in the hydrides a decade before us. So maybe a little, about a decade before us. And so we, it gave us what was going on with the tritium. Now we are, of course, looking at the helium in the next slide. This shows the helium-3 content that we got. And in here, for the helium-3, we had two types of measures. Open symbols were from NMR spin count. The solid symbols were from decomposition, mass spec analysis of the helium-3 that was released. And for the samples that were stored at minus 40, what we found was all the helium was retained in the material. But that, depending on the storage temperature, this is room temperature. After about 2 years, 40%, you saturated how much helium you would get. And at 75 degrees C, you were releasing a lot of helium, even at an early stage, and then over a period of time it would come out. 100 degrees C was somewhat more different. You were actually retaining a lot of the helium until some certain point, then you released it at a later time. What this showed was it was a fairly complicated temporal dependence of relaxation time and or concentration. And so we looked at it with relaxation time. Next slide. And what we did is we got different ages, and we looked at the time constant and the spin lattice relaxation time. All of them indicated that the heliums were in bubbles, but that the bubble size increased with temperature, just as we had seen with the tritium relaxation time. And that the numbers were here. I don't expect you to go through the numbers, but basically what we did is we collected the data, we did a comparison, and we concluded that had to be what was going on. So the next slide is sort of a summary of that. All this swelling that material was exhibiting is a combination of both molecular hydrogen and lithium metal as the dominant theme. That swelling occurs early before the helium-3 has a big effect. But that tritium and helium are trapped in bubbles. Presumably they share the same bubble. That would, if a bubble ruptures with tritium, it would release helium. The tritium in a closed container can react with lithium metal and reform. Helium will not, so it will do something different. The bubble size increases with temperature and with dose and age. We saw that same correlation. And that this helium outgassing is due to these bursting bubbles. The lithium metal formation, I don't show the data, but it was lagging behind. It has to, the metal moves more slowly, but it does form, and that there is a complex synergistic relationship. Some of the details we were published in a couple of papers. Both of these are with Clark Sowers and with myself. So about 20 years ago, we tried to summarize that. As far as I know, people haven't been looking at this material. Certainly haven't been doing the NMR that I ever saw, but it was an interesting example of this complex relationship. Lithium hydride was the most vulnerable of any of the materials we ever looked at for having damage from the tritium decay. Other metallic systems don't really do that. This ionic salt did. Now I want to talk a little bit about another material. This is uranium Tethy. This is a strongly paramagnetic material, and of course it had a lot of use not only at Mound but throughout the DOE complex for handling of tritium. It has a ferromagnetic ordering temperature about 183 degrees Kelvin, and this is an echo at room temperature for material. And this is a spin echo, and it's very sharp. It's not, like 23 microseconds. If you remember, the Helium-3 from Lithium Tritide was something like 500 microseconds. So what we have is the magnetic properties of the uranium hydride itself gives an inhomogeneous magnetic field that makes this time constant short. And what we did is we plotted that as a function of temperature, and we find that the T2 gets shorter as the temperature gets lower, and that it crosses just about where the ferromagnetic ordering temperature is. So it's a confirmation that it's the magnetic properties of the material determines this T2, the line spectra. But the next slide shows the helium concentration. There was no molecular tritium, but that we measured by both volumetric and NMR, and we counted how much helium and we see that for hundreds of days there's all the helium retained, and then it starts to come out being released. This is nomenclature accelerated release or hurried release. But these are 5 different samples collected data. These are the T1 relaxation time. These are the T2N, the carbon cell 1, and they start out very different. They become, over a period of a few hundred days, still, different, not all that different, only more than an order of magnitude different here to down to about a factor of 5. Again, showing that these were all measured there, and taking that the correlation is that as T2 approaches T1, that the bubbles are getting somewhat bigger. We're seeing a growing size, and then that they level off. They're leveling off here at the longest time. Next slide. And so this is that accelerated release, and this is the maximum helium concentration you can get, about 0.1 helium atoms per uranium atom in the material, and that we concluded that there is no helium in the lattice, that it is actually being released into bubbles. But these bubbles are very small. They're smaller than what they are in lithium tritide. They're on the order of 10 nanometers, and very high pressure, on the order of 10 kilobars or even greater. There's a distribution of bubble sizes by roughly an order of magnitude, but again much smaller than in, and that the size will change with time until they rupture and they release helium. That was a mechanism. Now we couldn't do much more with the uranium tritide, but we started looking at other tritides, and the next chart shows that. As I mentioned earlier, at the beginning, George Abel and others did a lot of work on the palladium. They actually analyzed this, and it's been reported that they could correlate that you're getting helium pressures up to 100,000 atmospheres within the solid. And there have been mechanisms proposed in the literature that basically when the tritium decays, it makes the helium, but the heliums are so unstable, they will push metal atoms away, collect in small bubbles, and then continue to collect helium in the neighborhood, and then the bubbles will grow and do that. And we did a correlation with other different materials. We got titanium, vanadium, a couple of alloys, and I put the data here. I figured after half an hour of seeing spectra, you're probably pretty tired of it. But it is there. We did publish a lot of this, and we have observed very similar behavior. There are differences in detail. Crystal structure matters. The main thing has to do with the relaxation times, the way the system. T1s are very short in uranium because it's paramagnetic. It tends to be very long in something that's more like a semiconductor, like magnesium nickel or lithium hydride. But that the overall relationship of the system is the same, particularly when the helium retention at room temperature, it's always always indicating that by the time NMR experiments can be done, the helium has been virtually all trapped in the bubbles and give characteristics of either small bubbles. And this ratio is that indication that they're small bubbles, that they grow, and that bubble size go roughly by a factor of 3 to 10. And that at some point, the ratios all become nearly constant. We're assuming that within the mechanical strength of the materials and the pressures being generated, that the system can no longer continues to trap helium, that there's a breakdown in the last, it releases the gas, and that's how it changes. And that there's a distribution of relaxation time. So that's pretty much how we concluded the behavior of helium-3 in metal tritides, and a lot of different examples. Now, the next slide, I mentioned that I took data, but so did Alatella and George Abel and Bart Kraft on hydrides and over the years. There were a lot of people here that made and handled samples for it. Henry Steinmeier and Ralph Yager and Wayne Tadlock, Dick Carlson, Terry Glob, Lyle Matson. They were all working on different projects, but they were doing samples and things that we got our hands on and did NMR. There were, of course, analytical. Ron Sprague did a lot, Ray Baker and Don Solinger in X-ray with the SW mass spec team. Joe Cantrell, who recently passed away, but worked on X-ray with me, particularly on the hydrides. He didn't work on the tritides, but we did a lot of work over the years on hydrides. And then, of course, early projects like Chuck Wiedenhap, Ken Foster, and Dick DeSanto, Gus Bambakitis with Wright State did analysis, worked a lot with George Abel when they were working on that. Ken Phipps was in charge of a lot of the work. And Don Kogo worked with George at Sandia Livermore on palladium work in the late 80s. In fact, Don is still analyzing data, still doing stuff on tritides. I was at a meeting a couple of years ago, and he was still there going strong, describing the mechanisms of helium formation and release out of metals. So he's still active in that. Again, we started looking at hydrides and tritides at Mound with NMR about 73, and it went on for almost 20 years. And there were actually results on hydrides published in journal articles as late as 2002. I still have, to be honest, a few results I would like to publish someday. I probably never will, but at least I still have notes of a few hydrides that I thought would be interesting to report. And the next slide, so I said, well, where are we in the whole field? Where is it turned out to be? Well, there's still tritides being used in the weapons complex for a variety of reasons. At Savannah River, Los Alamos, there's fewer than there used to be, but there's still interest in these materials. There's research in the U.S. and France, and there are papers published on property deuterium retention in metal, particularly related to fusion and some other techniques, so there's still at least some interest. However, the distinction is I've not seen any helium-3 NMR data for over 15 years. Mound developed and implemented a truly unique way to look at these materials and characterize them. When I mentioned Don Kogo, he's still analyzing and interpreting data that was taken almost 20 years ago. A different route is that there are, in the last 20 to 25 years, a variety of high-resolution solid-state NMR techniques that have been developed and implemented that are looking at hydrogen storage materials for these fuel cell vehicles. And that's what I've been involved with for the past several years, working with people at Caltech and some people at Washington University on that. But again, it's not tritium, but it is hydride, and it is very interesting in looking at a way. NMR is a very powerful tool to get a lot of information. And I think that maybe we go to the next slide. That's it, my formal presentation, and thank you.